Welcome to our lecture on polynomial rings. Today we are going to explore a beautiful mathematical structure that builds upon the basic algebra you already know. We will see how simple rules can create powerful systems used in modern technology. Whether you realize it or not, these concepts are working behind the scenes every time you use the internet. Now that we are ready to begin, let us imagine you are building a train. The variable x and its powers, like x squared, are just empty train cars acting as placeholders. The actual cargo you put inside these cars are numbers, which we call coefficients. Now, imagine a strict rule. All your cargo must come from one specific warehouse, like the set of integers. When you collect all possible trains built from that warehouse, you create a polynomial ring. We call the starting warehouse the base ring R, and the new universe of polynomials is denoted as R bracket x. Let us look at how we write this formally. This formula represents the entire polynomial expression. The symbols a0, a1 up to an are the coefficients. The core rule of the polynomial ring dictates that every single one of these coefficients must belong to the underlying base ring R. The symbol x is called an indeterminate, meaning it is not a specific number waiting to be solved for, but rather a structural placeholder. The non-negative integer n represents the highest power of x present, which we call the degree of the polynomial. If all coefficients are 0, it is simply called the zero polynomial. Knowing what a polynomial looks like, how do we add them? This formula shows exactly how we add two polynomials together. We simply take the coefficient ai from the first polynomial and add it to the coefficient bi of the second polynomial for every matching power of x. The crucial part here is that this addition operation happens entirely inside the rules of the original base ring R. Because the base ring is closed under addition, the new coefficient is guaranteed to also be in the ring R. This ensures that the sum of two polynomials is always another valid polynomial in the same ring. Addition is straightforward, but what about multiplication? This equation represents the rule for polynomial multiplication. It is the exact same distributive property, often remembered as the FOIL method, that you use in basic algebra, just generalized for polynomials of any length. The new coefficient ck is formed by multiplying and adding combinations of a and b coefficients, whose indices sum to k. Because the base ring R allows for both multiplication and addition, every new coefficient we create this way is perfectly well defined. If the variables increase in power, the formula simply scales up to accommodate them. To visualize this relationship, let us look at this diagram. The large circle represents the polynomial ring, R bracket x, containing full polynomial expressions. Notice the arrows pointing down from every single number, the coefficients, into the rectangular box below, which is the base ring R. The structure of the polynomials exists in the larger space, but every single numerical value attached to the variables is strictly sourced from the foundational base ring. The variables are just the scaffolding holding those numbers in place. Before we move on, let us see this with a concrete example. We will work inside the polynomial ring z bracket x, which means all our coefficients must be integers. We are given two polynomials, p of x equals 2 plus 3x and q of x equals 1 minus 4x. We are asked to find their sum. To do this, we place both polynomials side by side. We then group the constant terms together, 2 and 1, and the coefficients of x together, 3 and negative 4. This visual setup prevents mistakes before any arithmetic happens. Continuing with our addition, we now perform the arithmetic using the standard rules of integer addition. 2 plus 1 gives us 3 for the constant term. 3 minus 4 gives us negative 1 for the x term. These are simple operations happening entirely within the base ring of integers. Our final result is 3 minus x. Because 3 and negative 1 are perfectly valid integers, we have proven that the sum belongs safely inside our polynomial ring. Physically, this just means combining like quantities. Now let us tackle multiplication using the exact same two polynomials. We are asked to find their product. We place them next to each other in parentheses to indicate that every term in the first must multiply every term in the second. We start by distributing the 2 to both terms in the second bracket. Then we will distribute the 3x to both terms in the second bracket. This sets up our fully expanded form before any simplification takes place, ensuring we do not miss any terms. With the distribution set up, we now compute the individual products for all 4 terms. We multiply the integer coefficients using standard integer rules, and when multiplying the variables, we add the exponents of x together. The constants multiply to 2. The outer terms give negative 8x, the inner terms give positive 3x, and the final terms multiply to negative 12x squared. We now have a 4-term expression, and we must look for any terms that can be combined. To finish the multiplication, we need to look at the middle terms, specifically the negative 8x and the 3x. These are like terms because they share the exact same power of x, so they must be combined. Adding negative 8 and 3 gives us negative 5. Our final simplified product is 2 minus 5x minus 12x squared. Since 2, negative 5 and negative 12 are all integers, the product is a valid member of the polynomial ring. This represents the combined scaling of our original polynomials. Now that we have mastered standard integers, let us look at a polynomial ring with a twist. What if our base ring has unusual rules? Consider the ring Z2. In this base ring, the only allowed numbers are 0 and 1, and all arithmetic is done modulo 2. This means we only care about the remainder after dividing by 2. So 1 plus 1 equals 2, but since 2 divides evenly by 2 with 0 remainder, it becomes 0. The strange rules only apply to the coefficients. The variable x still behaves exactly as it always does. Let us see how modulo arithmetic changes things. We want to multiply two identical polynomials, f of x equals 1 plus x and g of x equals 1 plus x, under these strange new rules in Z2 bracket x. We are asked to find their product. We set up the multiplication exactly as we would in standard high school algebra. We distribute the terms to expand the expression fully, giving us 4 separate terms to evaluate. The variable behaves exactly as it always does. Continuing our calculation, we simplify the distributed terms to get 1 plus x plus x plus x squared. Next, we combine the like terms in the middle, adding 1x and 1x to get a middle coefficient of 2. In a normal polynomial ring, we would stop here and declare this the final answer. However, our coefficients must belong to the specific base ring Z2. We must now evaluate this coefficient of 2 under the rules of modulo 2 arithmetic to find its true value. In this specific base ring, the number 2 is mathematically equivalent to 0 because modulo 2 arithmetic only looks at the remainder. Therefore, the number 2 does not actually exist in this ring and must be replaced with a 0. Because the coefficient is 0, the entire middle term completely vanishes from the expression. Our final answer is simply 1 plus x squared. This beautifully demonstrates how changing the underlying base ring drastically alters the final outcome. You might be wondering, why do we care about polynomial rings in the real world? They are actually the absolute foundation of modern cryptography and digital communication. When your computer sends data over a noisy Wi-Fi network, it uses error-correcting codes. These codes work by treating your data as coefficients in a polynomial ring over a finite field. If parts of the message are corrupted by interference, the mathematical properties of these polynomials allow the receiving device to reconstruct the missing pieces perfectly. Let us summarize what we have learned today. A polynomial ring is simply a collection of polynomials where all coefficients are restricted to a specific mathematical ring. The variable acts as a structural placeholder, while the coefficients dictate the actual arithmetic based on the rules of their home ring. By changing the underlying ring, like moving from integers to modulo arithmetic, we can create vastly different polynomial behaviors. You have now covered the full topic, unlocking the mathematical tools used to protect and transmit digital information worldwide.